Alright, so we want to show that there is one and only one way of making an abelian group M into a Z module. So we want to show existence and uniqueness of this Z module structure. So for existence, given some k and z and little m and big M, define a map. And of course I'm going to write the map explicitly here, and you'll see why. We're going to phi of km is going to be equal to k times m. So on the left, this phi is the product that we're going to use, the map that's going to define our module structure. And then km on the right here, this is just if k is 0, then it's just 1, the identity of m. If k is a natural number, then it's just m added to itself k times. And if k is a negative natural number, then it's negative m added to itself k times. So it's just the normal, the way you, what is this? It's just you add m to itself k times, basically. And so, of course, the reason I'm actually explicitly using capital phi here is because otherwise I write this, we're going to define km to be equal to km, and when you look at that, you're like, that doesn't tell me anything about anything, because it's just a tautology. But no, that's not, writing that, you mean something differently with the left hand, the right side. Even though they are equal, the symbols are different, because when you write this, here the multiplication we're considering is what I just said. You add m to itself k times, and here you're suppressing the module structure, or you're suppressing the function that we're going to prove defines the module structure. So then let's prove that this works. Phi of 1m is just m. Phi of k plus l m is going to be k plus l m. And of course, if you take k plus l and add it to itself m times, then because z is abelian, you can flip those around. Wait. Yeah, you're taking m and you're adding it to itself. Well, yes, yeah. This is using abelianity of z. It's a cool word. That you can write this as km plus kl. And then from there, what is that abelian? You're not really moving things around at all. You're just grouping them differently. So instead of having m plus all the way up through m, k plus l times, you're considering it, you have it k times and then l times. But it doesn't matter however you want to see it. I feel like I'm going to spend a lot of time here talking about obvious stuff. But you have to be careful, especially in these early exercises when you're getting familiar with the definitions. A lot of times you have to talk about very easy stuff as if it's not easy. But then if you talk about easy stuff as if it's not easy, then you can talk about hard stuff as if it's not easy. And a lot of times the hard stuff is harder than the not easy way that you're talking about it. And so that's when you're making progress. Or actually using algebra to gain insight into things that are really difficult to understand. I hate this Z. I always have trouble drawing this. But anyways, okay, so this is good. What else do we have? Phi, here, I'm going to get rid of this. Don't need that. Phi of k and then m plus n equals k m plus n. And so this is where we're going to use that m is abelian, because this is just m plus n plus m plus n plus so on and so on. You have this m plus m n thing appearing k times, but then you got to move all the m's together and then all the n's together, and that uses the fact that m is an abelian group. So that is very important here. But anyways, we have this, and this gives us phi km plus phi kn, and the hardest one, but not really that hard in this case, klm is equal to, well, klm. Just going to write it like that. But you're just taking m and you're adding it to itself k times l times. So what you could do is you could think of it as like, oh, instead of adding m to itself k times l times, it's you take m and you add it to itself l times, and then you do that k times. And so this is klm, just because of how addition of an element by itself works in a group. And this is of course we're going back to the phi notation now. K of lm, phi of klm, k phi lm, and then this is phi of k with phi of lm. Okay. So phi defines n a z module m. Of course, left z module, but I mean, whatever. I'm always going to assume that they're left modules. I'm not even going to write it. Sometimes I'll write it. I might write it. Okay, so that's that. So that's existence. For uniqueness, suppose phi makes m a z module. So phi is a map that gives a z module structure on m. Hold on. Something on my screen. Okay, so now what? Psi makes m a z module. I claim. We want to prove that psi is phi. So if k is in n natural numbers, then, okay, what is phi of km? Obviously little m is in big M is normal. I'm not going to write it out. Well, this is just phi. No, these are psi's. Psi, guess I have to rewrite it. Sum from 1 to k of 1m. You just write k as you're summing 1 to itself k times. But because this is a module, this is the sum from 1 to k of phi of 1m. And because this is a module, we know that, okay, so if we're summing it by itself from 1 to n times, we're multiplying it by itself by k. We're adding it to itself k times, and then phi of 1m, because this is a module, is m. Okay, so that's that. And what if... So that takes care of natural numbers. What about negative numbers? Negative km. This is just the sum from 1 to k of negative 1 m. This is going to be similar. Equals, let's see here, sum from 1 to k of negative phi 1m. But that's just going to be negative k times m. combining these facts with phi 0m equals 0, where here 0 is the identity in m. Well, no. 0 times m. There we go. Yields that phi of km equals km equals phi of km. So psi equals phi. Okay, so we know that phi does make m into a left Z module, and any map that makes m into a left Z module is equal to phi. And so this completes the proof, because it establishes that phi exists, and it is the one and only one way of making capital M into a left Z module. And so that's exactly what we wanted to prove.